Okay, shall we start? Today is the final day of this workshop. The first speaker is François Legal, Graduate School of Mathematics, Nagoya University. The title is Dequantizing the Quantum Singular Value Transformation. Please start.
Okay, thank you. So today I will talk about results that appeared at the QIP this year about dequantizing the quantum singular value transformation and especially implication to quantum chemistry. And if I have time, to the quantum PCP conjecture. So it's a joint work with Sevak Garibia from Paderborn University. So if you have any question during the talk, please feel free to interrupt or send the question through the chat or really raise your hand, whatever. That's fine. Okay. So I will give you a one slide, very informal description of the result. And then I will give a more mathematically formal description of the result. But first, one slide. So we show many things, but the main application is in terms of chemistry, quantum chemistry, and in particular, we show that the central computational problem considered by quantum algorithm for quantum chemistry is BQP complete. So BQP complete means that it is as hard as simulating universal polynomial size quantum circuits. For example, as hard, at least if you can do it in polynomial time classically, then you can factorize integer efficiently. So it's a really unlikely that this will be possible. So this really gives theoretical foundations to claim the superiority of quantum algorithm for chemistry. And what problem is it? So I will give a formal version in the next slides. It's computing an estimation of the ground state energy of an Hamiltonian with inverse polynomial precision. Okay, when given a rough estimation of the ground state, because of course, if you don't know at all the ground state or don't have any approximation of the ground state, the problem is extremely hard. It's even harder than MA. It's what we call QMA hard. Okay, and as a second complementary result, we show that if instead of inverse polynomial precision, you are interested only in constant precision, then you can do it classically in polynomial time, so very efficiently. So this really shows that the superiority of quantum algorithms come from the improved precision that you can achieve in the quantum setting. So with inverse polynomial precision, you can do it with a quantum computer, but it's really expected that you cannot do it with a classical computer. But with constant precision, you can do it on a classical computer. And to prove the second result, we show how to dequantize the quantum singular value transformation. The quantum singular value transformation is a very popular method, very recent method for designing quantum algorithm. It has been proposed a few years ago. And we show that in some cases, in particular, if you're interested with constant precision, you can dequantize it. So transform it into a classical algorithm without losing too much in the complexity. And this dequantization result, which is the most technical and the main technical contribution of the work, has several applications, in particular to the quantum PCP conjecture, which is a central conjecture in quantum complexity theory. Okay, so I will start by giving a more formal description of the problem we consider, the results, and also the motivations. So quantum chemistry is considered as one of the most promising applications of quantum computers. And the problem that well, there are many problems that you want to solve in quantum chemistry, but one of the main problems can be described as follows. Compute a good estimation of the ground state energy of a local Hamiltonian representing the system, which in more mathematical terms precisely means compute a good estimation of the smallest eigenvalue of a sparse Hamiltonian matrix. Okay? And this is really interesting because this enables us to tackle this issue even without knowing much about quantum chemistry. I don't know much about the quantum chemistry. I didn't know anything before starting this project. But really, the problem that we want to solve can be written in this form, very easy to understand to mathematicians and computer scientists. And there are several approaches to solve this problem on the quantum computer. So the first most rigorous approaches were proposed by Lloyd, Abrams, Asparuh-Guzik, and several others. They are based on quantum phase estimation. So apply quantum phase estimation to get a good approximation of the ground state. The second kind of approach, which are very popular recently, are to use variational quantum algorithms. But this problem, these variational quantum algorithms are heuristically based. So it's not easy at all to analyze their performance in a rigorous way. So in this work, we only consider this rigorous approach based on quantum phase estimation. And I will explain this approach. But before this, I will introduce the main problem that we consider. So this version, formal version of what's written here. So you are given as input a sparse Hamiltonian acting on n qubits. Okay, so there are several ways of presenting this on a computer. You can assume that, for example, the Hamiltonian is local, and then you have a very short representation of the Hamiltonian, or you can give the Hamiltonian via an oracle. There are several ways. There are small technical details, so I won't talk too much about how this Hamiltonian is presented. But we don't have only an Hamiltonian, we also have a quantum state that has good overlap with the ground state of H. Okay, so you have a quantum state or a classical procedure to create this quantum state, and this quantum state has good overlap with the ground state of the Hamiltonian. And with these two inputs, you want to estimate the ground state energy. So even more formal, this is the really formal version, the problem called guided local Hamiltonian problem, GLH. So there are three parameters, S, epsilon, delta. So I will explain these three parameters. So the input is, as I said, a sparse Hamiltonian acting on n qubits. I assume that the Hamiltonian is normalized, and I use S to denote the sparsity parameter. So what does it mean? H is S sparse if each row or column contains at most S non-zero entries. Okay, so H is a very big matrix, exponential size, 2 to the n by 2 to the n, and you only the condition is that on each row, on each column, there are at most S non-zero entries. So typically, S will be polynomial in n. The Hamiltonian is exponential in n, the dimension, but the sparsity parameter will be typically polynomial in n. You also have a quantum state, U, and the premise is that this thing, the norm of this vector is at least delta. So what is this vector? It's a projection into the vector space spanned by the ground states of H. Okay, and the condition is that this projection is at least, the norm of this projection is at least the delta. So this is the meaning of good overlap with the ground state, an overlap at least delta. So delta is the overlap parameter. And finally, I want to find an approximation of LH. So LH is the ground state energy of H, the smallest eigenvalue. And I want an epsilon additive approximation. So I want to output a lambda tilde such that the difference between lambda tilde and lambda H is at most epsilon. Okay, so these are the three, it's the formal version of the problem with all the parameters S, delta, and epsilon.
Excuse me.
Yes.
What is the input size of the n-qubit quantum state? To the n, or
I will consider that we can consider that the state is given as a quantum state. So you have n qubits. So the input size will be n.
so input is given as a quantum state, not
quantum state.
Classical string.
It's a quantum state. So the input is quantum in this version.
Okay. Okay.
And if you don't like this, you can consider that your quantum state is given by a classical description. You have a classical circuit computing this quantum state.
In that case, classical string must be exponential in n.
Yeah, so, but it will be, you can, in that case, assume or put the promise that this the length of the circuit will be polynomial in n.
Okay, thank you.
Okay.
Thank you.
Do you mind if I also ask a question? I can understand physically why locality implies sparsity,
yes,
but in general, sparsity doesn't, at least intuitively to me, seem
you're
to
completely right. Yes, locality implies sparsity, but the other direction is not true. So we prove our result for sparse Hamiltonians. This gives you a more general result. But for physical application, it's perfectly okay to consider local Hamiltonians.
I see. Great. Thank you.
Any other questions? Okay, it's exactly that. If it is local, it will be sparse. So yeah. Okay, so now the relation with chemistry. Okay, so I will very, very briefly explain this rigorous approach to use quantum computer to solve problems from chemistry. Okay, so you have a physical system representing a chemical system. And the first step is to find the Hamiltonian corresponding to this system. So first, you have to use techniques like second quantization with finite size basis to get the Hamiltonian. And then you have to express it using qubits because you want to run that on a quantum computer. Quantum computer use qubits. So there are a lot of methods to do this. But the conclusion is that when you do it correctly, what you obtain is a sparse Hamiltonian, actually a local Hamiltonian, but it will be okay to consider only the statement that the Hamiltonian is sparse with sparsity parameter polynomial in n. Okay, for instances, in this paper, they get n to the 4 here with a few other conditions, n to the 2, and so on. Okay, so you get an Hamiltonian sparse with sparsity parameter polynomial in n. And then you need to find a good state. More precisely, a quantum state that has good overlap with a ground state. Okay, and given an Hamiltonian, finding a quantum state that has good overlap with a ground state is an extremely difficult problem. It's NP hard, it's even in QMA, so it's really horribly difficult. But the point is that for many concrete system in quantum chemistry, there are methods that give very good approximation. For example, the Hartree-Fock method typically, so typical here, very important word, recovers the 99% of the total energy. So it has overlap very, very large with this ground state eigenvector. Okay. And then you apply quantum phase estimation. you have an Hamiltonian, you have a good approximation of the ground state vector. Okay. And then you can use phase estimation, and what you will get is a good approximation of the ground state energy, the ground energy. Okay, and if you analyze precisely this approach with the parameter I mentioned, because you see that it's exactly an instance of this, you have an Hamiltonian sparse, you have a quantum state which has good overlap with the ground state, and you want an estimate of the smallest eigenvalue, then you observe that the running time is a polynomial in S, 1 over delta and 1 over epsilon. So in particular, when S is polynomial in N and delta epsilon inverse polynomial in N, this gives you running time polynomial in N. Okay. Okay, and I write one theorem that expresses the complexity here. So this problem again is this one. So what this approach shows is that when S is polynomial and delta epsilon at least 1 over polynomial, the problem, guided local Hamiltonian, can be solved in polynomial time with a quantum computer. Okay. Okay. And so for that reason, a lot of people claim that this is really a compelling evidence of the advantage of quantum computers for such problem, because it seems difficult to solve this using a classical computer. But is it really hard? It's not actually so clear. I don't think there was any formal proof of the hardness of this problem for classical computers. There are a few arguments saying that, well, it's based on phase estimation, and phase estimation is a very powerful technique that solves integer factoring and many other hard problems, but it's true. But the Hamiltonian on which you are applying phase estimation, in our case, is sparse. It's not the case for integer factoring. For integer factoring, the Hamiltonian is very, very dense. Okay, the matrix is very dense. Here it's sparse. So maybe when it is sparse, there is a very clever way of solving this problem classically. It's not really a good argument. The second one is we know that the problem is very hard if we don't have the guiding state. Okay, so you can assume that even if you have an approximation of the guiding state, it's still probably fairly hard. But it's not really, I don't think it's a convincing argument, because having a guiding state really significantly simplifies the problem. And I will give you a striking example, which is the following. When you are given exactly the ground state, okay, then you can compute exactly the smallest eigenvalue very efficiently classically. So, of course, the ground state is exponential size, so you have to make some assumptions. So assume that this exponential size ground state is given in a classical random access memory, where you can access any position you want in constant time. And assume that the first coordinate of u is not 0. Then it's extremely easy to compute the smallest eigenvalue, because it's equal to this ratio, the first coordinate of hu and the first coordinate of the vector u, this one, u1. And computing the first coordinate of hu is very easy, because h is sparse. So you have only a few non-zero entries in each row. So you only need to look at the few non-zero entries of the corresponding entries of the vector u, and you can compute this. So it will be very efficient if you have a nice representation of u. So if you know exactly the ground state, it's very easy classical. So the question is, what is the complexity of this problem when we have only an approximation, a fairly weak approximation of this ground state? And it wasn't so clear. So, but main result shows that this problem is hard for classical computers. It's BQP hard. So again, BQP hard means that if there exists a classical algorithm that solves this problem, then any quantum polynomial computation, for example, Shor algorithm, can be simulated classically very efficiently. So it's very unlikely. So the theorem says that this problem is very hard for classical computers. And for which parameters do we prove that? For S equal poly, so polynomial sparsity, for epsilon 1 over poly, and delta equal 1/2. So even if you have an approximation, a fairly good approximation with overlap 1/2, it's hard to get an inverse polynomial precision approximation of the smallest eigenvalue. And so I'm not an expert of quantum chemistry, but from what I understand in quantum chemistry, getting inverse polynomial precision is really the holy grail. Okay? So people doing quantum chemistry want to get precision less than the chemical accuracy. Chemical accuracy is a constant, a small constant. But in quantum chemistry, you don't consider normalized Hamiltonian. So when you normalize everything, your constant precision becomes constant over the number of qubits, so inverse polynomial. So this is precisely inverse polynomial precision, is precisely the regime that people doing quantum chemistry want to achieve. And so I believe that this gives some theoretical foundation to claim the superiority of quantum algorithms for chemistry. And the second result say that if now you only interested in the complexity when delta and epsilon are constant, then you can solve a problem in polynomial time using a quantum computer. Sorry, so using a classical computer. Okay, so if you have small constant, so if you have constant delta and epsilon, arbitrarily constant, can be any small constant, but shouldn't depend on n, then the problem can be solved on a classical computer. So this really shows that the superiority of quantum algorithms, so this theorem, really holds only for this parameter, the epsilon 1 over polynomial. If you put the epsilon to constant, then the problem can be solved very efficiently on a classical computer. Okay, so everything superiority of quantum algorithm really comes from the improved precision achievable in the quantum setting. And this is really the main discovery of this work. So are there any questions before I give a very short overview of the proof of the two results? Okay, so then I will give a one slide, very brief overview of the proof of hardness. So the proof is fairly standard in the sense that we want to show that the problem is BQP hard. So we want to show that if we can solve efficiently this problem, we can solve any problem solved by a polynomial sized quantum circuit. So what we do, we take a polynomial sized quantum circuit, and from the circuit, so we need to show how to efficiently, classically, create a sparse Hamiltonian and a states with good overlap with the ground state of this Hamiltonian. such that a solution of the guided local Hamiltonian problem with that input gives information about the output of the set. This is the standard approach, proving the hardness via reduction. Okay? And to create this instance of the guided local Hamiltonian problem, we use a Kitaev circuit to Hamiltonian construction. Okay, this is essentially all I will say about the proof. So there is a technique introduced by Kitaev et al. That enables you to map a circuit to an Hamiltonian so that the eigenvalues, especially the smallest eigenvalues of the Hamiltonian, give you information about the output of the circuit. And this is exactly what we need. Okay, so we use a similar construction, and then you have to carefully create the states that has good overlap with this the ground state of the Hamiltonian coming from this construction. And there are a few subtleties, you need more work and so on. But this part is a little bit technical, so I won't say more about it. Okay, and I will now explain a little bit this second result. So now we have delta and epsilon constant, and I want to show that the problem can be solved efficiently with a classical computer. And so what does it mean? So if I want to design a classical algorithm for that, I cannot say any more than the input is a quantum state, because a classical computer cannot get a quantum state. So what you need is to input an efficient classical representation of the quantum state. And there are many possibilities. And what we will use in this work, we will use the same assumption as in all these prior works by Tang and subsequent works, all these works on dequantization, where you assume that quantum state can be accessed classically via L2 sampling. Okay, so you have the vector u here, exponential length, and you assume that you can perform L2 sampling from this vector. So what is L2 sampling? This means that one sample, when you ask for one sample, you will get a pair IUJ, IUI, and you will get it with this probability. Okay, so one sample gives you this pair, I, the index, and the corresponding entry with this probability. Since the norm is 1, this really gives you a probability distribution. Okay, this corresponds essentially of what happens if you measure the state quantumly, except that quantumly, of course, when you measure it, you don't get the UI. Here, we're assuming that you get the UI. Okay, and otherwise, it's exactly the same. Okay, so I will explain how this works. So here, the original problem is to compute an estimate of the smallest eigenvalue. I will consider a decision version. It's a little bit easier to explain the approach using this version. They are essentially equivalent. Okay, in the decision version, I only ask you to decide whether the smallest eigenvalue is smaller than A or larger than B for some A and B. So A is strictly smaller than B. Okay, and I have a promise that it is either smaller than A or larger than B. And to do this, I will explain how the quantum singular value transformation solve this problem. But to do this, I need to introduce a few notations. So first, H is Hamiltonian, so I can write its eigenvalue decomposition like this. The norm is 1, at most 1, so all the eigenvalues become minus 1 and 1. And the smallest eigenvalue, the ground state, will be the first. eigenvalue here, so sigma 1. And then for any polynomial, you can apply the polynomial on H. And there are several definitions, so all equivalent, but this is equivalent to applying the polynomial to each eigenvalue here. Okay? And there is a method that I mentioned briefly at the very, very beginning of the talk, the quantum singular value transformation. And the quantum singular value transformation can be described as a method to apply this thing, this matrix, to a quantum state. There are a few difficulties. So first, this matrix is not a unitary matrix. So you have to interpret it as a unitary matrix. And there's a method to do it, which is a qubitization, which means encoding the matrix PH into a block of a larger unitary matrix. It's a method qubitization, but it's not really very important. The point is that it's a method that enables you to apply this thing on a quantum state. It was defined in this paper. It was shown that you can do dequantization in some cases, but only for very low rank matrices. Okay, and the tool to apply this powerful technique in order to solve this problem is this lemma. The lemma from Low and Schwang in a very influential paper that actually introduced quantum singular value transformation. So there exists a polynomial Q of degree 1 over b minus a, such that, well, this condition holds. It's probably much easier if I write a few things. So what you have is, here you have x, you have minus 1, 1, 0, and you have a somewhere and b somewhere. And what I'm saying is that, so the value of the polynomial is between 0 and 1 in this region, between minus 1 and 1. And if it is smaller than a, it's very close to 1. So here it will be very close to 1. Here it's 1. And when it is larger than b, it's very close to 0. And between a and b, it can be arbitrary. Of course, it's a polynomial, so it's not very, very bad, but it can be anything. There is no condition in the intermediate region, except that the values are between 0 and 1. Okay. Okay. And now the crucial equations are here. So what's happened if you apply this polynomial Q on H, so this H, and apply this matrix on the U here? So there are two cases. The first case is when lambda H is very large. So lambda H equals sigma 1 is very large. So all the other eigenvalues are also here, which means that the polynomial is almost a zero polynomial in this area. Okay? So this means that here you will get a 0 or something very close to 0. The second case is when you have lambda H smaller than A. So in that case, you will have this inequality because we know that U has non-negligible overlap with the ground state. And for the ground state, the eigenvalue is this. And for this eigenvalue, you have almost 1, polynomial evaluate to 1. So you will get at least here your delta. Okay? So you have to distinguish between this case and this case. And so I need to probably to erase this drawing. And the quantum singular value transformation is a technique that enables you to distinguish these two cases. It's a very clever technique with this complexity. And what we show is that actually classically the same thing can be done with this complexity. So you have S here, and you have the 1 over b minus a, which is in the exponent. Before it was as a polynomial here, term of the polynomial. No, it is in the exponent. And there's also a term in delta, but I'm ignoring it. So I'm putting the complexity when delta is constant. What does it mean? This means that when S is polynomial, delta constant, and constant AB, that means b minus a constant, then the whole term here becomes polynomial. So the running time of the classical algorithm is polynomial as well. Okay, which is exactly what we wanted to prove. And how do you prove this theorem? It's really by analyzing this. So QH, so H is a sparse matrix. Q will be also, Q is a polynomial of this degree. So you can show that QH is a matrix which is still reasonably sparse. The sparsity parameter is this. So of course you get this in the exponent. And then given a sparse matrix and a vector U, L2 something access to vector U, you have to show how to estimate the norm. And this is something that can be done with a recent technique on dequantization. And if you do it carefully, you can show that indeed you can check which of the two conditions. Okay, so the key parameter in the complexity is really the sparsity of QH. And since the degree of Q is this, the sparsity becomes this. Okay. And yes, so I also have some connection with the quantum PCP conjecture, but I don't think I have time, and it's a little bit technical. So it has some applications. I will jump to the conclusion. Okay, so again, it's essentially the same slide as the first one. So we consider a central computational problem for quantum algorithm for quantum chemistry, which is computing an estimation of the ground state energy with inverse polynomial precision, given a rough approximation of the ground state. And we show that this problem is hard for classical computers, BQP complete, BQP hard. And so this gives theoretical foundations to claim the superiority of quantum algorithms for chemistry. And we have a second result. We really show that if your required precision is only constant, you can solve the problem classically in polynomial time. So this really shows that the superiority of quantum algorithms come from the improved precision achievable in the quantum setting. With inverse polynomial precision, you can do it on a quantum computer, but not on a classical computer. But with constant precision, you can do it on a classical computer. And to prove the second result, we show how to dequantize the quantum singular value transformation with constant precision. Okay. And the last point, which I didn't really mention in detail, is that this result gives a new perspective on the famous quantum PCP conjecture, which is one of the central conjecture in quantum complexity. And a few open problems. The first one, well, they are a little bit technical, but so we showed that the hardness for delta equal 1/2. So we would like to improve that, showing the hardness even for delta very close to 1. The second one is the sparsity. We showed that it's hard to solve the problem even with actually 6 local Hamiltonians. And I would like to improve that and show the hardness even for 2 local Hamiltonians, which is probably the weakest class that we can consider. The second open problem is that while we are showing the hardness in the theoretical way, the Hamiltonian we use in our proof are fairly artificial. So it will be very important to try to show the hardness for the Hamiltonian really occurring in quantum chemistry. And the last one, which is a little bit difficult to approach. So we showed, so there is, as I mentioned, another approach to quantum chemistry, which is based on variational quantum algorithm. It's more heuristic. And it will be really nice to try to give theoretical foundation for the superiority of quantum algorithms there too. But of course, it's only heuristic. So it's not clear how to approach this question. Okay, so it's all what I wanted to say. Thank you for your attention.
Thank you very much for very nice talk. Is there any question or comment? Please, Arthur.
I was just clapping. Thank you for the talk.
Thanks.
Any question? I'm wondering this approach can characterize other complexity class, for example, BQL.
It's a good question. Yeah, I think the same approach can be applied to, well, you would have to restrict the number of qubits, the size of your system. Now you have polynomial number of qubits. You would like probably to put logarithmic number of qubits.
Yes.
And you can, of course, implement the phase estimation. So the upper bound will work. So for the first, this one, yeah, probably this theorem expecting phase estimation approach, you will have a version that works also. So you have an upper bound, quantum upper bound on what you can do. And you would like to show the superiority here. So the question is whether you can use the Kitaev reduction from circuit to Hamiltonian, even in the setting where you are only a small number of qubits. And I think it should be possible, yeah.
Oh, okay.
Yeah,
oh.
But I haven't really thought about it. But it's probably a nice question. Yeah.
Oh.
Logarithmic space, or even something between logarithmic and polynomial, polylog, and so on. Yeah.
Okay, thank you.
Actually, if there is time, I do have a small question.
Sure.
It's
you mentioned this construction of Kitaev, and I was just a little bit curious. You didn't want to get into technical details, and I guess I don't want you to either. But can you just say a little bit more about what you mean by the construction recovers some kind of information? I just didn't really get what mathematical input do you have and what mathematical output do you have? And what is the relationship between the two?
Sure, I have slide for that. Yes, so yes, so it's okay, it's here. So you have a circuit, and from a circuit you want to create an Hamiltonian that express the output of your circuit. So you can assume that the output of the circuit will be only one bit. You measure only one qubit, it's a 0 or 1. And if the probability of getting a 1 is high, then you want the smallest eigenvalue of your Hamiltonian to be large. And if the output of your quantum circuit is 0, you want the smallest eigenvalue of your Hamiltonian to be very small, say 0. And Kitaev shows that it's always possible to do it by creating an Hamiltonian that represents some kind of constraints representing the computation. So you express a whole computation as a series of constraints. So initial state to be the O0 state. The first step of the computation should be the application of this matrix. The second step, this matrix. You encode everything in a fairly artificial way into a big Hamiltonian. And you show, so you really have to see the proof. It's very beautiful. Then when the output is 0, then the smallest eigenvalue is exactly 0. And when the output is 1, the smallest eigenvalue is actually fairly large, 1 over polynomial or even larger. Okay, so it's a technique which is very beautiful. It has been extremely useful. Even a lot of hardness result I proved in this way.
I see. Thank you very much.
It's okay. Thanks.
Other question or comment? If not, let's thank speaker again. Now, the next chair is Francois,
Yes.
I think.
Yes, I think we have maybe a few minutes, but maybe the next speaker can share the slides and prepare.
Can you see my slide?
Yes. We will wait maybe 2 or 3 minutes. Or we can start, but probably better to wait a little bit because some people can join. Do you wish to put your slides full screen or is it full screen? Yeah. Okay, so maybe we can start. So the next speaker is Yongcheng Yao. It's a joint work with Kelly and Masahito Hayashi, and the title of the talk is Tight Exponential Analysis for Privacy Amplification. So please.
Okay. Thanks to the organizer for giving me the chance to give this talk. I'm going to present you our work, Tight Exponential Analysis for Privacy Amplification. This is a joint work with Curly and Masahito Hayashi. Let me start it. This is the outline of this work. I first introduce the motivation of our work. Then I turn to our research problem and the main results. Finally, I conclude with some summaries and open questions.
Excuse me, so maybe you can share your video if you have a video on.
Okay.
Probably better for.
Is it okay?
Is it okay? I don't see all your face. I see only the bottom part. Okay, okay, perfect. Okay, thank you. Thank you.
Our work comes from the study of the error exponent of for the classical channel as one of the most important theorems in classical information theory. Shiner's second theorem says that the sender can transmit the classical information to the receiver with asymptotically vanishing error. If and only if the transmission rate is less than the channel capacity. Although Shiner's second theorem can ensure the reliable communication asymptotically, however, in realistic setting, we can only use finite channels. Hence, determining the optimal error when the number of the channel is finite is more practical. When the transmission rate is fixed and less than the channel capacity, the optimal average error among all schemes with the fixed rate converge to zero exponentially. The exact exponent of this decay is defined as the error exponent of the classical channel. If we can determine the expression of the error exponent, we will calculate the approximation of the optimal error when the number of the channel is sufficiently large. Determining the error exponent for classical channel has a long history. This problem has not been completely solved until now. Here are two important contributions for this issue. Gallagher had derived a lower bound for the error exponent by applying an elegant random coding technique. Under that, Shannon, Gallagher, Burley-Camp derived an upper bound for the error exponent, which is called the sphere packing bound now. If we compare the graphs of these two bounds, we can find that the random coding bound matches the sphere packing bound when the transmission rate is larger than this critical value. Hence, we can determine the exact expression for the error exponent in the high rate region. However, when the transmission rate is below the critical value, neither the random coding bound nor the sphere packing bound is the exact expression for the error exponent. And increasingly work imply that the tools in combinatorics is more powerful in the low rate region. The above introduction is our motivation. Now I turn to our work. Our research focuses on the error exponent for privacy amplification. Privacy amplification is a vital step in quantum key distribution. In the process of quantum key distribution, after some steps of preparing the key, Alice and Bob share a pair of raw key, which is correlated with the adversary. And the initial state can be described by this classical quantum state. That Alice and Bob applies a hash function to their raw key. They hope to extract a pair of secret key, which is uniform distributed and independent of the adversary. The performance of the scheme is characterized by the security measure between the final state and the idle state. The security measure can be chosen as many forms. Commonly used security measure includes the trace norm distance, purified distance, and the salvaged running relative entropy. For n copies of the initial state, when the key rate is less than the conditional entropy of this state, there exists a sequence of hash functions such that the performance of these schemes converge to 0 as n tends to infinity. And the error exponent for privacy amplification is defined as the optimal rate of exponential convergence under which the performance asymptotically approaches the perfect. In our work, we studied the error exponent under the purified distance security measure under the salvaged running relative entropy security measure. The salvaged running relative entropy was first put forward in these two papers as a generalization of the classical running relative entropy. It has nice properties and is important in many quantum information processing tasks. As later shown, the error exponent for privacy amplification is characterized by the salvaged running conditional entropy. When the parameter alpha tends to 1, the corresponding salvaged running relative entropy converges to the Umigagi relative entropy. The Umigagi relative entropy and the purified distance are two commonly used measures in quantum information theory, especially the Umigagi relative entropy. It appears in various tasks and has operational meaning. In this part, I briefly introduce the smoothed max relative entropy and our first main result. The smoothed max relative entropy is defined for two states, rho and sigma, which represents the minima among all max relative entropy between the states in the epsilon neighborhood of rho and sigma. In privacy amplification, the maximum number of extracted key when the allowed error is below a threshold epsilon can be characterized by the smoothed max relative entropy. So investigating the asymptotic behavior of the exponential decay of the small modification in smoothing the max relative entropy is crucial for the study of the error exponent for privacy amplification. In our work, we first deal with this issue. Specifically, our research object is this smoothing quantity. That is the minimum purified distance between rho and such some normalized states rho tilde. We did one-shot analysis for this quantity and derived an upper bound and a lower bound for it. From these two one-shot bounds, for n copies of rho, sigma, and a constant r, we can determine the exact decay rate of exponential convergence of this smoothing quantity. It's characterized by the salvaged running relative entropy. Now I briefly explain that how do we use the exponent of smoothing the max relative entropy to derive an upper bound for the error exponent under the purified distance security measure. First, we can prove the monotonicity of the smoothed conditional mean entropy under the action of hash functions. That is, for any hash function f, we have the smoothed conditional mean entropy of the initial state is larger than that of the result state. From this inequality, it's easy to verify. The relation 1 is equivalent to the following inequality 2 about this two smoothing quantity. And from equation 2 and the definition of the smoothing quantity, we can obtain that the optimal performance for one initial state is larger than this smoothing quantity. Hence, for n copies of the initial state and a fixed key rate R, its optimal performance is larger than the corresponding smoothing quantity. From the relation 4 and the exponent of smoothing the max relative entropy we had derived, we can directly get an upper bound for the error exponent under the purified distance security measure. This upper bound is characterized by the salvaged running conditional entropy. Hayashi had derived a lower bound for the error exponent in 2015. This lower bound is in this form. We compare the expression and the figures of our
Please back. Could you back? Previous slide. So this is the direction of inequality is incorrect, I think. Lower bound. Direction of inequality.
Yes, I made a mistake. This is larger than the lower bound, not less than.
Thank you.
Any other questions? Okay. We compare the expression and the figures of our upper bound and Hayashi's lower bound. It's clear that our upper bound matches the lower bound when the key rate is larger than this critical value. And when the key rate is below the critical value, we can give some counter examples to show that neither the upper bound nor the lower bound is the correct expression for the error exponent. Hence, our result exhibits a similar picture to the error exponent for the classical channel. Our next result is about the error exponent under the salvaged running security measure. We first use the random coding technique to derive an upper bound for the one-shot optimal performance. That is, for a classical quantum state rho xe under two universal random hash functions f, for any s between 0 and 1, we have the expectation of the performance is less than this expression. From this relation, for n copies of the initial state and a fixed key rate r, we can derive a lower bound for the error exponent. Then, by using a large deviation analysis method, we can obtain an upper bound for the error exponent. Both these bounds are characterized by the salvaged running conditional entropy, and they are matched when the key rate is larger than a critical value as well. Hence, we also can get the exact expression for error exponent in the high rate region. The above introduction is our main results. Finally, I conclude with some summaries and open questions. In our work, we derive the error exponent for privacy amplification and several important security measures, including the purified distance and the salvaged running relative entropy. For the first time, we provide operational meanings for the salvaged running relative entropy in characterizing how fast the performance of quantum tasks approaches the perfect. And here we have some open questions. The first question is the error exponent for privacy amplification below the critical rate. Similar to the channel coding setting, determining the error exponent is below the critical rate is a very difficult problem. We currently know almost nothing about this issue. I think we need more tools in combinatorics to solve this problem. And the second question is the error exponent under the trace norm distance. The trace norm distance is an important security measure in privacy amplification. Determining the error exponent under this measure is also a difficult but interesting problem. I think that's all. Thank you for your listening.
Thank you very much for the very nice talk. So, are there any questions? So I do have a question about your previous slides, the summary slide. So the question 2 is to characterize the exponent under trace norm. So you mentioned that it is difficult. So why is it more difficult than for other distances? Can you give it some intuition?
I think the difficult under the trace norm distance is that we can't find optimal hash function to such that the performance and the trace norm distance can achieve this exponent because in the purified distance and the salvaged running relative entropy in these two security measure, we only use the random coding technique. We can determine efficiently upper bound, and from this upper bound of the performance, we can obtain the tight lower bound of the exponent. But in the trace norm distance, the random coding technique is not suitable. We need to find a hash function, found a suitable hash function such that the performance can decay with this exponent.
So sorry, I want to comment. So please show me theorem 2. Please show me theorem 2. Please. Okay, yes. Please. Theorem 2. Theorem 2. Theorem 2. Theorem 2. Theorem 2.
P2 嘛?
No, theorem 2. Second theorem.
Second theorem.
Maybe theorem 2.
Which page? Which page?
Final page is very
final page. Oh, okay.
maybe,
this page.
Maybe a little bit before. Yes, 1 or 2 before that.
2 before. 2.
Previous one. Previous. Yes, this one.
This one. So, first of all, if we take trace norm, even in the classical case, this problem is still difficult. In the classical case, I discussed that problem. So then we have some different result. Once we consider universal hash function, so under the condition for universal hash function, this is randomization. In that case, the exponent minimum is solved in the classical case. However, if we choose the deterministic one, there is some possibility that exponent become better. For example, there is no side information. We have only one sequence. In that case, the problem can be considered as randomness extraction. So in that problem, that random hash function and deterministic situation, we have a different exponent. So due to that problem, even in the classical case, if we consider that somehow deterministic one, so we don't have that tight exponent. So then it is impossible to solve that problem directly in the quantum setting. So maybe impossible, I think. Firstly, we need to solve an easier case.
Sure.
But this is still experimentally difficult. So in that case, usually we consider another story. We consider our hash function to be the universal to hash function. That setting is much more easy. So in that case, I already solved that problem in the classical case. But still, its quantum extension is quite difficult. However, if we take another security measure, in that case, there is no difference between the randomized case and deterministic case for exponent. This is quite strange. So the result somehow depends on the security measure.
Okay, thank you for the very clear explanations. So are there any other questions?
can I ask a question?
Yeah, sure.
Okay, could you show me what's the definition of Wei rho? Yes. I mean, no, the Wei rho, the function Wei rho. No, not this one. Yes. Yes, here, or V sigma. Okay. Okay, thank you. Okay, thanks.
Any other questions? Fine. Okay, then see if there is no further question, let's thank the speaker. And move to the next talk. So thank you. So the next speaker is Hayato Arai from Nagoya University. So could you please share your slides?
Okay. Can you hear me?
Yes.
And can you see this slide?
Yes.
With the pointer?
Yes.
Okay.
Okay, so I said maybe we can start a little bit early, but we can maybe start now, and this will give us more time for the lunch break. Okay.
Okay.
Okay, so I will just, the next speaker is Hayato Arai. So it's a joint work with Masahito Hayashi, and the title is Pseudo-Standard Entanglement Structure Cannot Be Distinguished from Standard Entanglement Structure. So please.
Thanks to introduce and organize our talk. This is a joint work with Masahito Hayashi. If you know the detail of this talk, you can see it on this archive. At first, we give a brief summary on this talk. This talk is addressed on general probabilistic theories, and our interest is with the characterization of entanglement structure. Entanglement structure is a possible structure of quantum composite system in GPTs. In standard quantum theory, the structure of composite system is uniquely determined by the tensor product. However, in GPTs, the structure is not uniquely determined, even if the local systems are completely equivalent to the standard quantum theory. Here, we introduce a kind of structure almost like the standard entanglement structure called shade standard entanglement structure, and consider the problem that is there any example of shared standard entanglement structure except for the standard entanglement structure. Our result possibly answer this problem. That is, we show that there are infinite examples of the shared standard structure. Also, we show that some of the examples of shared structure can discriminate non-orthogonal state partially. And besides, we investigate a variation of entanglement structure with group symmetry. And we show that a kind of global unitary symmetric condition determines entanglement structure as a standard one uniquely. Okay, let's start to talk about details. First, for mathematicians, we give a strict definition of the positive cone that has an important role in GPTs and also our setting. But to understand only this talk, you don't need to remember this definition hereafter. Anyway, a positive cone is a subset of real vector space satisfying these three conditions. Simply speaking, positive cone is such a cone, like green color or blue color, whose vertex is 0. This set corresponds to the set of non-normalized state space. And mathematically, positive cone derives a kind of positivity In GPTs, we can generalize a model of quantum theory by dispositivity. And next, we explain our setting. As a preliminary, we remember the definition of complete system of standard quantum theory. In this talk, we consider finite dimensional Hilbert space with the same dimensional local Hilbert system and use this notation as a set of Hermitian matrices and positive semi-finite matrices. And here we consider this setting, density operator state and P of M measurement. The important thing is this equivalent condition. The condition, an element of measurement is positive, can be translated as this property condition, this positivity condition. In this way, the standard entanglement structure is defined by the set of positive semi-definite matrices. And hereafter, we call this model the SES. And the definition of entanglement structure is a generalization of the SES. That is, we consider a positive cone K instead of the set of positive semi-definite matrices. Some natural operational postulate implies that the positive cone K satisfies this inclusion relation. Here, SEP is the set of all separable elements, and its dual is defined as a set of all positive elements, all positive element for any element in SEP.
Sorry, can I ask, just to understand this definition, what is SEP star in the case of quantum theory?
A quantum theory is a set is equivalent to the set of all entanglement of witness.
Okay, thank you.
Thank you. So in this setting, the state is defined as a anomalous element in K, and the measurement is defined as dual element valued measure. Sorry, not P of M, dual valued measure. So of course, this definition doesn't determine the SES uniquely because this not uniqueness. So our motivation is the characterization of the SES from these entanglement structures. Actually, the SES has some special properties. First, self-duality. That is, the cone K and its dual cone is equivalent. Here we remark that the dual is defined as such set. Especially the element of dual is also considered as Hermitian matrix. And many entanglement structures are not self-dual, and therefore sometimes they have extraordinary behavior. Also, the SES has a symmetry of global unitary operation, and that is any pure state is generated by unitary operators from a single pure state. In mathematics, self-duality and homogeneity derive as a structure of Euclidean algebra. And similar characterization also holds, that is, self-duality and some symmetric condition derives the SES. However, it is open that the symmetric condition is essentially necessary. That is, there any self-dual entanglement structure except for the SES, it is open. Also, we have a question that is there more operational characterization? So in this talk, we consider operational characterization by repeatability and verification of maximally entangled state. And now we simply give the relation, introduce the repeatability and the relation between repeatability and pre-duality. So repeatability is a physical postulate that ensures post-measurement state cannot be changed by the sequence of the same measurement. Such postulate implies the injective correspondence from an effect to a state. And therefore, a model with repeatability satisfies this inclusion relation. Here we call this property pre-duality. And then we obtain the following theorem for any given pre-dual cone K. there is a self-real cone satisfying this inclusion relation. Simply speaking, a pre-real cone can be modified as a self-real cone. In the proof of this theorem, we apply Thorne's lemma, and therefore the self-real modification is not constructive. And due to this weakness, it is difficult to show that two self-real modifications are strictly different, even if the pre-real cone, two pre-real cone are strictly different. This problem is resolved by the following theorem. Simply speaking, when we obtain exact hierarchy of pre-real cones, then we obtain strictly different self-real cones, tilde ki. So in this way, repeatability and self-duality is connected by our theorem. And next, we introduce a verification condition. We consider a verification of maximally entangled state in an entangled structure K, because the error probability of verification is estimated by the trace norm. We define the value D of K as this. This means how small error we can verify to exist maximally entangled state in the structure K. For example, if D of K is equal to 0, then K contains all maximally entangled states. That is, theoretically, we can verify to prepare all maximally entangled states in K, in the system K. So then we consider the condition D of K is less than epsilon. And we call this condition epsilon undistinguishable condition, because this condition implies that we cannot deny the possibility of the structure K by preparing a maximally entangled state with epsilon error verification. And we introduce epsilon shade standard entangled structure hereinafter epsilon PSES as an entangled structure with self-duality and epsilon undistinguishable condition. The standard structure is an example of epsilon PSES for any epsilon larger than 0. Our question is that, is there any other example of epsilon PSES for small epsilon? This answer is yes. Next, we explain our results. We show the existence of epsilon PSES by main theorem 2. In order to apply main theorem 2, we need to construct an exact hierarchy of pre-real cones. In our paper, we construct a pre-real cone KR with a parameter R larger than 0. And we can show the family of KR composes an exact hierarchy of pre-real cones. And we can show that the self-real modification to the KR is exactly different. Also, we can estimate the value of D of K tilde KR as follows. So the important thing is when the parameter R goes to 0, then the value of D of KR also goes to 0. Therefore, we obtain the following theorem. That is, for any epsilon larger than 0, there exists infinite example of epsilon PSES. As a concrete construction of pre-real cones is given as follows, but this is very complicated. In detail, you can see all on our archive paper. But simply speaking, we construct pre-real cones like this by the convex hull of a subset of positive matrices and a set of non-positive matrices with a certain form by using the set of maximally entangled orthogonal bases P. P is a subset of the set of all maximally entangled orthogonal bases. Next, we explain additional result about the non-orthogonal state discrimination. State discrimination is a fundamental task in quantum information theory. In GPTs, distinguishable states are defined similarly to quantum theory as follows. In the sense, low k are distinguishable if and only if they are orthogonal. However, we showed that for some P0, for some epsilon PSE, for some examples of epsilon PSEs we constructed before, there exists a measurement and perfectly distinguishable states such that they are non-orthogonal. Therefore, so our preceding studies shows that some non-self-real entanglement structure has also a non-orthogonal distinguishable states. Therefore, we give a conjecture that orthogonal discrimination characterizes the sets. That is, any self-real entanglement structures or any epsilon PSEs, except for the sets, contains non-orthogonal distinguishable states. In our paper, we give explicit construction of the measurement and the distinguishable states. In details, please see the archive paper. And finally, we explain the result about the entanglement structures with group symmetry. In this talk, we consider the following two subgroups of general linear group on Hermitian matrices. First one is the global unitary group, and second one is the local unitary group. Here, local means the tensor product of unitary operator on subsystems. And we introduce a condition, G symmetry. That is, a given cone K satisfy that the G of X belong to K for any X in K and Z in the group. Then we show the following theorem. For any entanglement structure K, they are equivalent. K is G symmetric, and K is equal to the set. This is equivalent condition. The GU symmetry is weaker condition than homogeneity. Therefore, this result relaxes the assumption of characterization of the sets when we compare the result about the algebras. When we consider entanglement structures. So when we restrict the considered cones to the entanglement structure. Here, this theorem implies that symmetric condition is essential for the characterization of the sets. However, GU symmetry is not operationally natural so much, and more natural symmetric condition is LU symmetric, because the aim of the characterization of entanglement structure is how we determine the structure of a composite system by local structure and local operation. Then, this is an open question. The combination of self-reality and epsilon undistinguishable condition and LU symmetry can determine the sets uniquely. That is there LU symmetric epsilon PSEs except for the sets? This is open question. So we summarize this talk. In GPTs, there are many possibilities of entanglement structures. Especially, we introduce the epsilon PSEs as an entanglement structure with self-reality and epsilon undistinguishability. Then we show that there exists infinite example of epsilon PSEs for any epsilon larger than 0. Also, we give some result that implies two important open problems. First, some epsilon PSEs can discriminate non-orthogonal state perfectly, which implies the possibility that orthogonal discrimination can characterize the sets. This is an important open problem. And second, we show that GU symmetry characterizes the sets from entanglement structures. However, it remains open whether there exists LU symmetric PSEs except for the sets. That is all. Thank you for your attention.
Thank you for the very nice talk. So are there any questions? Okay, so I have one question about the open problems you mentioned. So they are really very interesting open problems. So I would like to know what is your intuition there. Do you believe that the answer is yes? Or no?
It is very difficult question, but important question. Thank you. So I think these conjecture might hold when we impose additional some very weaker condition. But whenever we when we never impose some additional condition, the open the conjecture is we don't know. I don't have an idea as whether the conjecture holds or not.
Okay, but
because,
you don't have any idea about the counterexample either.
Yes.
No.
But because the class of the entanglement structure or the class of the possible cone is very, very larger. So there might be some very complicated counterexample or not. So
okay, yeah, I find the question really interesting. So if you have any progress, I will be really happy to hear.
Thank you.
Okay, so any other questions?
I have some comments. So, of course, in this presentation, maybe the meaning of self-duality very clear. Maybe ordinarily could understand this and correspond to the repeatability. But the epsilon undistinguishability, the explanation of the epsilon undistinguishability is somehow complicated. How about your impression, Luca, about this concept? Maybe not so easy. So this epsilon means the amount of approximation. So approximation to the standard entanglement structure. So epsilon is quite small. So in that case, it is very difficult to distinguish that given pseudo entangled structure and from the standard entangled structure. So, for example, our quality of precision is if assume that when our quality of precision is epsilon, in that case, we cannot distinguish between the cis and given entangled structure. So, in this sense, you cannot distinguish these two entangled structure. So somehow that kind of pseudo entangled structure behave as true standard entangled structure. So in that sense, we have a very, very small epsilon undistinguishable pseudo entangled structure, almost impossible to distinguish a true entangled structure. So in this sense, this epsilon is quite serious. So once that structure, our structure satisfy, pseudo structure satisfy repeatability, self-duality, but if this one does not satisfy epsilon undistinguishability, so in that case, we can easily deny such kind of pseudo standard entangled structure by using our experiment. But usually our experiment has a limitation of the precision. Due to that kind of limitation, it is very difficult to distinguish that kind of pseudo structure and true structure. So in this sense, we found that kind of pseudo entangled structure with very, very, very small epsilon. So this is due to that reason. So even for we have a good experiment, we cannot distinguish that kind of pseudo structure. So in this sense, this one is a very serious theoretical problem.
Yeah, I understand your point here. Yeah.
Thank you, clear explanation.
Thank you. Any other questions, comments? So if not, it's precisely time. So let's thanks Hayato again. And this is really the end of the morning session. So the next session will start as usual at 2:30 Japan time and 1:30 Chinese time. Okay, thank you.
Thank you very much. So now we have free discussion time. So